In this section, we will learn how to identify the null hypothesis and the alternative hypothesis when given a claim about a population parameter such as a proportion or a mean. In conducting a hypothesis test, we will calculate a test statistic, find a critical value, calculate a p-value, and state a conclusion that addresses the original claim. In this section, we present key components of a formal hypothesis test. The concepts in this section are general and apply to hypothesis tests involving proportions and means and standard deviations or variances. In statistics, a hypothesis is a claim or a statement about a property of a population. A hypothesis test or a test of significance is a procedure for testing that claim about a property of a population. The property of a population is often the value of a population parameter. Some examples of typical hypotheses or claims include the mean body temperature of humans is less than 98.6 degrees Fahrenheit. Or the proportion of consumers who are not comfortable with drone deliveries is greater than 0.5. Let's consider this example. 1,009 consumers were asked if they are comfortable with having drones deliver their purchases, and 54%, or 545, of them responded with no. Using P to denote the proportion of consumers not comfortable with drone deliveries, the majority claim is equivalent to the claim that the proportion is greater than half, or P is greater than 0.5. The expression P greater than 0.5 is the symbolic form of the original claim. The big picture. We have the claim that the population proportion P is such that P is greater than 0.5. Among the 1,009 consumers, how many do we need to get a significantly high number who are not comfortable with drone delivery? A result of 506, or 50.1%, is just barely more than half. So 506 is clearly not significantly high. A result of 1,006, or 99.7%, is clearly significantly high. But what about the result of 545, or 54.0%, that was actually obtained in the Pitney Bowes survey? Is 545 or 54% significantly high? The method of hypothesis testing allows us to answer this question. It's easy to obtain hypothesis testing results using technology. The screen displayed here shows the results from 4 different technologies, so we can use computers or calculators to do all the computational heavy lifting for us. However, we also know how to manually calculate all of the results needed to conduct a hypothesis test. Examining the 4 screen displays, we see some common elements. They all display a test statistic of z equals to 2.55, which has been rounded, and they all include a p-value of 0.005, which has also been rounded. Focus on understanding how the hypothesis testing procedure works and learn the associated terminology. Only then will results from the technology make sense. Hypothesis tests are also called tests of significance. In Chapter 4, Section 1, we use probabilities to determine when sample results are significantly low or significantly high. This chapter formalizes those concepts in a unified procedure that is often used throughout different fields of application. This flow diagram summarizes the procedures used in two slightly different methods for conducting a formal hypothesis test. The first step is to identify the claim. The second step is to give symbolic form. The third step is to identify the null and the alternative hypotheses. The fourth step, we select our significance level. For our fifth step, we identify the test statistic. For step 6, we have to choose between two methods, the p-value method or the critical value method. With the p-value method, we find the value of the test statistic and the p-value, and then we draw a graph and show the test statistic and the p-value. With the critical method, we find the value of the test statistic and the critical value. We draw a graph showing the test statistic, critical values, and the critical region. For step 7, we make a decision, and we either reject or fail to reject our null hypothesis. And finally, for step 8, we restate the decision in non-technical terms. The object of steps 1, 2, and 3 of the flow chart is to identify the null hypothesis and the alternative hypothesis. The null hypothesis is a statement that the value of a population parameter, such as a proportion, mean, or standard deviation, is equal to some claimed value. We denote the null hypothesis with an H and a subscript 0. The alternative hypothesis is a statement that the parameter has a value that somehow differs from the null hypothesis. We denote the alternative hypothesis with an H and a subscript 1, or an H and a subscript A. For the methods of this chapter, the symbolic form of the alternative hypothesis must use one of these symbols, either less than, greater than, or not equal to. Confidence intervals and hypothesis tests are similar in that they are both inferential methods that rely on approximated sampling distributions. Confidence intervals use data from a sample to estimate a population parameter. Hypothesis tests use data from a sample to test a specified hypothesis. If we construct a confidence interval, and if our confidence interval contains the value claimed by the null hypothesis, then our sample result is close enough to be the claimed value, and we therefore do not reject our null hypothesis. If our confidence interval does not contain the value claimed by the null hypothesis, then our sample result is different enough from the claimed value, and we would therefore reject the null hypothesis. Let's review the steps of hypothesis testing in context of our drone example. Step 1. We identify the claim to be tested and express it in symbolic form. Step 2. We give the symbolic form that must be true when the original claim is false. Step 3. We consider the two symbolic expressions obtained so far. We have the alternative hypothesis H1, and it is the one not containing the equality. So H1 uses the symbol less than, or greater than, or not equal to. The null hypothesis is the symbolic expression that the parameter equals the fixed value being considered. Recall that our drone example states the following. 1,009 consumers were asked if they were comfortable with having drones deliver their purchases, and 54% of them responded with no. Using P to denote the proportion of consumers not comfortable with the drone deliveries, the majority claim is equivalent to the claim that the proportion is greater than half, or P is greater than 0.5. The expression P is greater than 0.5 is the symbolic form of the original claim. Given the claim that the majority of consumers are uncomfortable with drone delivery, we can apply steps 1, 2, and 3 as follows. Step 1. Identify the claim to be tested and express it in symbolic form. So using P to denote the probability of selecting a consumer uncomfortable with drone delivery, the claim that the majority is uncomfortable with drone delivery can be expressed in the symbolic form as P is greater than 0.5. Step 2. We give the symbolic form that must be true when the original claim is false. If the original claim is P is greater than 5 is false, then P is less than or equal to must be true. In step 3, we identify the alternative hypothesis H1 and we identify the null hypothesis H0. Using the two symbolic expressions P greater than 0.5 and P less than or equal to 0.5, the alternative hypothesis H1 is the one that does not contain the equality. Of those two expressions, P greater than 0.5 does not contain the equality. So we get the alternative hypothesis H1 is P greater than 0.5. The null hypothesis H0 is the symbolic expression that the parameter equals to the fixed value being considered. So our null hypothesis is P equals to 0.5. In step 4, we identify the significance level of alpha. The significance level alpha for a hypothesis test is the probability value used as the cutoff for determining when the sample evidence constitutes significant evidence against our null hypothesis. By its nature, the significant level alpha is the probability of mistakenly rejecting the null hypothesis when it's true. So we can say that the significance level alpha equals to the probability of rejecting H0 when H0 is true. Continuing with step 4, the significance level alpha is the same alpha that was introduced in Chapter 7, Section 1, where we defined the critical value. Some common choices for alpha are 0.05, 0.01, and 0.10, with 0.05 being the most common alpha level. In step 5, we identify the test statistic that is relevant to the test and determine its sampling distribution. Its sampling distribution could be a normal distribution, a t-distribution, or a chi-square distribution. The table on this slide lists the parameters along with the corresponding sampling distribution. We can use this table to identify the test statistic that is relevant to the test and determine its sampling distribution. For example, if the parameter is a proportion P, we might have a sampling distribution that is a normal or a Z distribution. If we had a population mu, the sampling distribution might be a T distribution. Again, if we had a population mu, we might have a sampling distribution that is a normal or a Z distribution. And finally, if we had a standard deviation sigma or a variance sigma square, our sampling distribution would be a chi-square. Recall that the claim P greater than 0.5 is the claim about the population proportion in our drone example. So we'll use the normal distribution provided that the requirements for the normal distribution are satisfied. Step 6 is the step where we find the value of the test statistic and either the p-value or the critical value depending on the method we choose. But let's go ahead and use the p-value method for this example. The test statistic is a value used in making a decision about the null hypothesis, and it is found by converting the sample statistic, such as p hat, x bar, or s, to a score, such as z, t, or chi-square, with the assumption that the null hypothesis is true. Getting back to our example, we have the claim made about the population proportion P. We have N equals to 1009 and X equals to 545. So P hat is equal to X divided by N, which is equal to 0.540. With the null hypothesis of P equals to 0.5, we are working with the assumption that P equals to 0.5, and it follows that Q equals to 1 minus P, which is equal to 0.5. So we can evaluate our test statistic as follows, where Z equals to P hat minus P divided by the square root of P times Q over our sample N. This equals to 0.540 minus 0.5 divided by the square root of 0.5 times 0.5 over 1009. This gives us a p-value of 2.54. The test statistic of Z equals to 2.55 from each of the previous technology displays is a little more accurate than the results we obtain in this formula. The critical region, or the rejection region, is the area corresponding to all values of the test statistic that cause us to reject our null hypothesis. Depending on the claim that we are testing, the critical region could be in the two extreme tails, or it could be in the left tail, or it could be in the right tail. And so we can say the following. For a two-tailed test, the critical region is in the two extreme regions or tails under the curve. A left-tailed test, the critical region is in the extreme left region or tail under the curve. And for a right-tailed test, the critical region is the extreme right region or tail under the curve. In a hypothesis test, the p-value is the probability of getting a value of the test statistic that is at least as extreme as the test statistic obtained from the sample data, assuming that the null hypothesis is true. Going back to our drone example, we can use the test statistic we calculated using technology or the test statistic we calculated by hand using our formula. Let's use the test statistic calculated using technology. Using the data from the previous problem, the test statistic is Z equals to 2.55. Assuming our distribution has a normal distribution, the area of 0.0054 is to the right of our Z value. So a right-tailed test with a test statistic of Z equals to 2.55 has a p-value of 0.0054. Go back and review the different technology displays given earlier and note that each of them provides the same p-value of 0.005 after rounding. To find the p-value of the hypothesis test, we first want to find the area beyond the point of the test statistic. If we have a left-tailed test and the critical region is in the region to the left of the tail, then the p-value is equal to the area to the left of the negative test statistic. If we have a right-tailed test and the critical region is in the region of the right tail, then the p-value is equal to the area to the right of the positive test statistic. If we have a two-tailed test and the critical value is in the region that is split between the left and right tails, then the p-value is equal to the area to the left of the negative test statistic plus the area to the right of the positive test statistic. It's important that you don't confuse a p-value with the parameter p or the test statistic p hat. So know the following notation. P-value is equal to the probability of a test statistic that's at least as extreme as the one obtained. Small p is equal to the population proportion. Small p hat is equal to the sample proportion. In a hypothesis test, the critical value or critical values separate the critical region, where we reject the null hypothesis, from the values of the test statistic that do not lead to the rejection of the null hypothesis. Getting back to our drone example, recall that the claim is that the majority of consumers are uncomfortable with drone delivery, so we will be conducting a right-tailed test. In this figure, you can see that the critical region is shaded in green. This graph shows that with a significance level of alpha equal to 0.05, the critical value is z equals to 1.645. In step 7, we make a decision to either reject the null hypothesis or fail to reject the null hypothesis. Under the decision criteria for the p-value method, we can say that if the p-value is less than or equal to alpha, we reject the null hypothesis. Or we could say if the p-value is greater than alpha, we fail to reject the null hypothesis. In step 8, we will restate the decision using simple non-technical terms. In other words, without using technical terms not understood by most people, we will state a final conclusion that addresses the original claim with wording that can be understood by those without knowledge of the statistical procedures. Now let's put all of the steps for our drone example together. Step 1, we state the claim that the majority of people are uncomfortable with drone delivery. If the original claim of p greater than 0.5 is false, then p less than or equal to 0.5 must be true. So let's move to step 3. Step 3 is in two parts. We can identify the null hypothesis and we identify the alternative hypothesis. So we can state that our null hypothesis, H0, is p equals to 0.5. And our alternative hypothesis, H1, is p is greater than 0.5. In step 4, we select our significance level of alpha. For this example, we set alpha equal to 0.05. In step 5, we determine that we are using the p-value method. So in step 6, we just calculate our test statistic. Let's calculate it by hand again. So we have z equals to p hat minus p over the square root of p times q divided by n. And this equals to 2.54. So what we have is a right-tailed test with a test statistic z equals to 2.54 and has a p-value of 0.0054. So in step 7, we make our decision to either reject or fail to reject our null hypothesis. Because our p-value is equal to 0.054, it is greater than our significance level of 0.05, so we will reject the null hypothesis. And finally, we draw our conclusion. And we could state that there is sufficient evidence to support the claim that the majority of consumers are uncomfortable with drone delivery. For help with wording for our final conclusion, refer to this table. This table lists 4 possible circumstances and their corresponding conclusions. Note that only the first case leads to wording indicating support for the original conclusion. If you want to support some claim, you state it in a way that it becomes the alternative hypothesis and then hope that the null hypothesis gets rejected. So if our condition is that the original claim does not include the equality and you reject H0, then the conclusion would be there is sufficient evidence to support the claim that, and then restate your claim. If the condition is that the original claim does not include the equality and you fail to reject the null hypothesis, you would state that there is not sufficient evidence to support the claim that, and then state your original claim. If the condition is that the original claim includes the equality and you reject the null hypothesis, you would say that there is sufficient evidence to warrant a rejection of the claim. And finally, if the condition is that the original claim includes the equality and you fail to reject the null hypothesis, then you would state that there is not sufficient evidence to warrant rejection of the claim. We should say that we fail to reject the null hypothesis instead of saying that we accept the null hypothesis. The term accept is misleading because it implies incorrectly that the null hypothesis has been proven. But we can never really prove the null hypothesis. The phrase fail to reject says more correctly that the available evidence isn't strong enough to warrant a rejection of the null hypothesis. Note that the final conclusions can include as many as 3 negative terms. For such confusing conclusions, it's better to restate them to be more understandable. Instead of saying that there is not sufficient evidence to warrant rejection of the claim of no difference between 0.5 and the population proportion, a better statement would be, until stronger evidence is obtained, continue to assume that the population proportion is equal to 0.5. A confidence interval estimate of a population parameter contains the likely value of that parameter. We should therefore reject a claim that a population parameter has a value that is not included in the confidence interval. In some cases, a conclusion based on a confidence interval may be different from a conclusion based on a hypothesis test. The p-value method and the critical value method are equivalent in the sense that they always lead to the same conclusion. The table displayed here shows that for the methods included in this chapter, the confidence interval estimate for a proportion may lead to a conclusion different than from the test of hypothesis. When testing a null hypothesis, we arrive at a conclusion of rejecting the null or failing to reject the null. Our conclusions are sometimes correct, but sometimes they are incorrect. With hypothesis testing, there are two types of errors, and we will distinguish between them by referring to them as type 1 error and type 2 error. Type 1 error is the mistake of rejecting the null hypothesis when the null hypothesis is actually true. The symbol alpha is used to represent the probability of a type 1 error. So we say that alpha is equal to the probability of a type 1 error, or it is equal to the probability of rejecting the null hypothesis when the null hypothesis is true. A type 2 error is the mistake of failing to reject the null hypothesis when it is actually false. The symbol beta is used to represent the probability of a type 2 error. So we can say that beta is equal to the probability of a type 2 error, or beta is equal to the probability of failing to reject the null hypothesis when the null hypothesis is false. This table summarizes the possible outcomes for a hypothesis test. There are 4 possible outcomes when we draw a conclusion based on our hypothesis test. First, we can reject the null hypothesis, but in reality, the null hypothesis is true. This scenario is a type 1 error. Second, we can reject the null hypothesis, but in reality, the null hypothesis is false. This scenario would be the correct decision. And third, we fail to reject the null hypothesis, and in reality, the null hypothesis is true. This scenario would also be a correct decision. And fourth, we fail to reject the null hypothesis, but in reality, the null hypothesis is false. This scenario would be a type 2 error. Let's look at this example. Consider the claim that a medical procedure designed to increase the likelihood of a baby girl is effective, so that the probability of a baby girl is p greater than 0.5. Given the following null and alternative hypotheses, we can write the statements describing a type 1 error and a type 2 error. So our null hypothesis would be p equals to 0.5, and our alternative hypothesis would be p greater than 0.5. A type 1 error is the mistake of rejecting a true null hypothesis. So the following is a type 1 error. In reality, p equals to 0.5. But the sample evidence leads us to conclude that p is greater than 0.5. In this case, a type 1 error is to conclude that the medical procedure is effective when in reality it has no effect. A type 2 error is the mistake of failing to reject the null hypothesis when the null hypothesis is false. So the following is a type 2 error. In reality, p is greater than 0.5, but we fail to support that conclusion. In this case, a type 2 error is to conclude that the medical procedure has no effect, when in reality, it is effective in increasing the likelihood of getting a baby girl. The power of a hypothesis test is the probability of 1 minus beta, where beta is the probability of rejecting the null hypothesis when it is actually false. The value of the power is computed by using a particular significance level of alpha and a particular value of the population parameter that is an alternative to the value assumed true in the null hypothesis. You can run a power analysis for many reasons, including 1, to find the number of trials needed to get an effect of a certain size. And this is probably the most common reason for running a power analysis. It tells you how many trials you need to avoid incorrectly rejecting the null hypothesis. You could also run a power analysis to find the power given an effect size and the number of trials available. This is often useful when you have a limited budget, say for 100 trials, and you want to know if that number of trials is enough to detect an effect. You can also run a power analysis to validate your research. Conducting power analysis, simply put, is good science. Also, calculating power is complex, and it is usually always performed with a computer. This is the end of Chapter 8, Section 1. Next week we will cover Section 2 and Section 3.